Okay, this is the first lesson on voltage, current, and charge, in which we're going to deal with the main definitions of these terms. First, starting with charge. We can look at charge in two basic ways. From a particle idea, we can view electrons and protons as having an intrinsic property of charge. An electron has a negative charge. A proton has a positive charge. The individual charges of an electron or proton are very small in comparison to the number of protons and electrons in an overall material. But if we consider an overall material, it will have some number of protons and some number of electrons. If the number of protons and electrons is equal, then that material is neutral. If the material has lost electrons, there are more protons than electrons, making the material positive. And if the material has somehow acquired extra electrons, there are more electrons than protons, making the material negative. The number of protons in a material rarely change except for cases of nuclear reactions, and as a result we consider the overall number of protons in a material to be constant. When scientists were making up the idea of charge, they didn't know how big an electron was or even that electrons existed. And so they had to make up some sort of arbitrary measure of charge that could be used as a standard unit. This is similar to the idea of a meter, where somebody decided on a length that was going to be a meter, and that was considered the standard meter from that point forward. Later, when they discovered the electrons, they discovered that they made 1 coulomb of charge, or the base unit of electrical charge, very large. It worked out that there are 6.25 times 10 to the 18 electrons, and essentially what this means is that there are more electrons than you could possibly imagine in 1 coulomb of charge. Alternatively, we can look at this from the point of view of 1 electron, in that 1 electron will have a charge of 1.6 times 10 to the negative 19 coulombs. Here we can see an equation that basically outlines how we can use the number of electrons This could be the number of extra electrons in the case of a negative object, or the number of removed electrons, or the deficit of electrons, in the case of a positive object. The given equation will show how to use the charge per electron to come up with the total charge of the material. An analogy to this would be, say, the cost of 1 apple is 50 cents. E represents the cost per apple. N then would represent the number of apples. And Q is the total cost of apples or total charge. Now if we, for example, have a positive object and a negative object, And remember our basic law of electrostatics, that unlike charges attract. Then if we connect these two materials with some sort of conductor, a conductor being a material that let electrons move freely, then the electrons in the negative object will naturally want to flow towards the positive object, and so they're going to try and travel this way. If we set up a toll booth along the highway and we counted the number of electrons that move through the circuit per unit time, then we would come up with an idea for the current of the material. But recall, as I mentioned earlier, that back when they made up all of these ideas or all of these concepts of electricity, they didn't know that electrons existed. And so instead of using the number of electrons, they had to just use the charge because they didn't know that there were electrons. Charge is measured in coulombs. Time is typically measured in seconds. And so current was given the unit amperes, named after the scientist who came up with all this stuff. And 1 ampere is equal to 1 coulomb for 1 second. Finally, voltage. Imagine two different situations. Here we have an object that's just a little negative. And an object that's similarly just a little positive. Alternatively, we could have a situation with an object that's very negative and another object that's very positive. In this situation, we can see that there's a greater difference between the number of electrons in each scenario. Sorry, this is a large negative. And this is a large positive. If we imagine conducting or adding a conductor in these two situations, the electrons moving in scenario 1 will want to go from the little negative to the little positive a little. Unlike charges still attract, like charges still repel, they still want to make the movement from one material to the other material, but it's not that important to them to make the move. Alternatively, if we consider the situation with a lot of negatives and a lot of positives here, then an electron traveling on this booth will want to travel a lot. Now imagine our toll booth situation again, and we can imagine how much we could charge this electron to get from one side to the other side. Here maybe we could charge them $1. And here maybe, because they want to go more, we could charge them something like $5 without them complaining. This is a situation of a small voltage. A small difference in the number of electrons at different points in a circuit makes the electrons want to travel from one point to the other point a little bit, in proportion to the small amount. As a result, the energy per unit charge that's released when the electrons do move from one point to the other point is relatively small. In this case, in the analogy we've used, the amount of money, for example, charged by that toll booth might represent the voltage or the amount of energy that we can get out of each unit of charge or each electron moving from one point to the other. On the other hand, in the situation where we have a big disparity between the number of electrons at the original point and the number of electrons in the final point, the electrons want to travel a lot. That's a large voltage. The difference in as a result, you can charge a lot more for the electron to move from one place to another, or in terms of energy, we can say that we can get a lot more energy per unit of charge that moves between the 2 points in the circuit. That hopefully gives you a conceptual understanding of current, voltage, charge. We're going to follow this up with a video that relates all of these things to Ohm's law and resistance.